right in the mouth. All right, second to last talk, and you guys are here. You're motivated, informed, and surprisingly sober. So, are you feeling okay? And good for you, right? So, thank you for staying to the second last talk. My name is Angsui from Rebel Security. We have, I guess, a lot of stuff to cover, so I'm going to skip through a whole lot of this stuff. We're talking about, oh, I know, so this is a presentation by the Rebel Security Special Effects Club, which we have founded. Okay, so we're talking about cryo-mechanical memory extraction. It's kind of like code boot, but I'll talk about the nuance. And now that I'm actually putting slides and presentation material together to talk about this work, I had some time to reflect on the last 2 years where we were doing this on and off, in the back burner. But the greatest philosopher of all of humanity once said, I can't see him coming down my eyes, so I gotta make these slides cry. Jay-Z, anyone, right? And then I couldn't help myself, so, well, I couldn't make these, cryo, Alright, there you go. So what is this? This is a story of failure, of 7 months of continuous, non-stop, soul-crushing failure that was embedded in a much larger, longer scope project of greater failure that had a tiny, epic point of win that we eventually got to after about 18 months of pretty much failing through every challenge and then actually working through it. So what was the challenge? What do we win? Okay, so, well, we actually just published 2 papers, one at Woot and one at Host. The first paper at Host was about the vulnerabilities that we found through this hardware and firmware reverse engineering on Siemens S7 PLC CPU controllers. And the paper at Woot is, that's the paper if you're interested in the details of how we put together this CNC control system that extracts memory. That is the paper that talks about all of these details. But, why do we do this? What do we do? What is the actual win? So here on the left side is, this little bar here is the global market share for Siemens in terms of industrial control. You kind of, depending on the day, the year, the continent, on average, they have about, a third of the world's industrial control systems market share, right? And this was the vulnerability that eventually became disclosed through the research. We worked with Siemens for about, more than a year to get this thing finally out. And, it reads, missing immutable trust, root of trust for CPU devices. Okay, so why is this? I mean, it's like a 4.6, is it a big deal? So, wait, There's a second page. Alright, there's a third page. Wait, there's a 4th page and a 5th page and a 6th page, 7th, 8th, 9th, 10th. So, it took me a long time to cut and paste every one, but this is a vulnerability that affects every single modern S7 1500 PLC CPU that exists. And this is the official workaround. Okay. Restrict physical access. Okay? That's it. And the official, what are we going to do about this? Every single model that they made up to the time of the disclosure, it's, what is it? No current fix, F off. Right? So I thought, I'm reading this email wrong, there's no way that that's the actual answer here, but yeah, this is a major portion of the global industrial control system, and that at this point, this is, I don't want to hype it up, but one of the pretty important forever days that is stuck in our infrastructure that's probably not going anywhere until all of the, S7 1500s get replaced in the world, which is probably between, the next 7 years to never, right? So, yeah, I think in this sense, it was a really cool technical achievement for the researchers, but I do believe in this case, this was an inexcusable lose for the world, because now we're stuck with this infrastructure, and that's not a joke. Anyway, so I have another talk about that, so let's get to what do we really do? Okay, so the real trick of it is we had to stare at that piece of hardware until it cried uncle, and it took us 18 months. And you look at it and you're like, well, that doesn't look complicated, it's pretty small, it's got 5 chips, how hard could it be, right? So, Why is this a big deal? Like I said, the 1500 line, like this is their primetime PLC CPU. Like I said, 30% of the market share. So, you would say the primetime line of CPUs of 30% of the market share, estimate XYZ, like it's got to be certainly single digit, maybe even double digit of the entire world's industrial control thing as we live right now, right? And also this line of product came into service around 2012, which was 2 years after Stuxnet went wide. So I don't know, maybe they took some notes and had to reconsider their secure computing for the hardware, right? Maybe not doing Stuxnet 2 again. So, they did a lot of really good things on this hardware. I didn't say security-wise, they did good things. So what do? It's very custom, right? If you look at it, there are 2 chips that just says Siemens, and the rest of it says F off, right? It's a very integrated design, so, you're not looking at components like an ASIC and then, like an FPGA that with clear labels and functional sort of separation on the board. You have 2 big old rectangles that does most of the thing, and you have a flash chip that's at stock, and then, some RAM chips that are also stock. But, they did a really good job on what I call product finishing when we look at, embedded devices. And it's not, designing a secure architecture for security on the hardware, but they removed everything useful for debugging and reverse engineering, right? Everything from no labels on any of the pins or pads, obviously no working JTAG, no UART, basically zero way for the attacker or the reverse engineer to interact and introspect the system in any meaningful way, aside from hit the button, wait for the LED to come on until the PLC ladder logic is writing, right? There was just very little way that we can actually, we can stare at the board, but we couldn't see what it was thinking, right? And that was very frustrating because, the finishing, this is a good thing to delay reverse engineering, but, it does actually nothing for the security architecture, right? So this is a good thing. I would recommend people do this as the very last step of their design, but as a reverse engineer, this kind of just pisses me off. It wastes my time, right? I know there's code inside, and I need to get to it, and I'm looking at the thing, and no obvious debugging interface. So, now we're making the typical decision of okay, what do we do now? Well, we can shake it, we can throw electrons at it, we can pulse it, we can glitch it, right? The standard palette of options are on the table. But then I said, maybe let's get above this game a little bit and maybe build something that is generic and automatable that kind of, basically transcends this level of time wasting, aka hardware finishing, at least in this kind of device. So I don't know if you guys remember Face Off, right? This is my Nicolas Cage. So I one night said, I'm tired of this. I don't want to glitch on this thing. I want to build a robot to take the memory of this computer and take it off. And then read it on an FPGA because, this is cute. I don't have all day. But then again, this thing took 2 years, right? So, I did have, 600 plus days. But, so the idea is if we can mechanically, just power up the system, mechanically remove the memory at a specific time, and this is dynamic memory. So, make sure the content of that memory doesn't disappear when it's powered down. And then somehow magically put it back onto a thing like an FPGA that speaks, a looser implementation of the DDR state machine, then maybe we can just read its memory, right? And then see what it's, what the code is running, and also this, the dynamic data, register values, and all of that stuff, maybe somewhere in this chip. So we're going to take the memory off. And then, then I talked about this idea to a few people, and what they said? They said, yeah, that makes sense. I've totally read that paper. The code boot attacks are well documented and well known, right? Because I think everybody remembers this paper. It's an epic, excellent paper. But aside from the awesomeness of the idea that it introduces, and the idea is that if you freeze dynamic memory, right, you can exploit, why does dynamic memory data evaporate when you power it off? It has a refresh cycle, right, that uses energy. So if you cool the chip, you're reducing the internal resistance of the cell, and then you're actually taking advantage of the data remnants effect, where you can, if you cool it down, you can actually power the device, the RAM chip down, and keep the content of memory in that chip and readable, not for seconds, but actual dozens of minutes, right, if you do it right. So that was a really cool idea, and this was the original paper, and I just want to point out, right, like, that is the level of scientific quantitative analysis that is a human hand with, like, compressed, CO2 gas can turned upside down, pointed at a defenseless ThinkPad with a nipple mouse, right? So then we said, okay, well, cool. If it's so well known, how do we do the left to the right, right? So the first challenge is, why come you don't have DIMM slot, right? So this paper initially was basically spray the cold thing onto the memory, pull it out of the DIMM slot, and then, like, write your own little bootloader, and then reinitialize all of this x86 hardware to get your memory to read on another computer. So, like, we looked at it and we're like, our computer doesn't have a DIMM slot. It uses so in this case, this was a LPDDR1. We also did it on 2 and 3, and 4 is also, I think, very possible. But this was just, like, the first obvious problem of how do we execute concept, right? Like, with reality. And then, like, when we started thinking about it for, like, literally more than a second, it got more and more complicated, right? So, sure, it doesn't have a DIMM slot, but guess what? Like, it doesn't have an interface. Like, you have to desolder the thing, which requires, last time I checked, either heat or, like, a miracle or something, right? Or vibrations, which cause heat. And then, after that, well, on top of this, there are 5 memory chips. And I love Germans, right? Like, and I was like, there's no way they would actually use 5 because they have to waste some bits, but you did. So 3 of them are on top, 2 of them on the bottom of the board, and they're all striped simultaneously because, like, this is a custom memory controller that uses, 4 chips, with error correction on it built in, not into the memory hardware, but in the controller itself. So here's the problem, right? Like, how do we cool the chips? How do we pull all the chips off simultaneously? Because you can imagine, right? Like, and also, by the way, like, the bit distribution on the chips are not, like, rational. I mean, it is rational from the perspective of routing, right? But the first chip doesn't hold bits 0 through 7 of the 32-bit word. It doesn't come close to doing that, right? They just kind of, like, put the memory chips where it was convenient for routing, and the actual bits themselves were all jumbled. So you can imagine, like, if we try to take one chip off and another chip off, right, you're taking, like, not just, like, we get a slightly offset view of, like, one byte in a word. You're getting, like, random bits changing, right, from different runs of the thing. And also, like, if you magically build a thing that can, like, rip 3 of the chips off and keep the thing, what happens when the memory chips on the bottom fall off because it's so hot, right? And also you have to cool it, by the way. So this was the challenge, and we did it, and we did it for under $1,000, and that's kind of the point of this talk. So get to the punchline. Like, I only have half an hour for this talk, so I'm gonna kind of just skip to the right answer and to kind of cheat a little bit. This was an intermediate build, and this was basically this works. Okay, so here we have a CNC. This is a highly, like, professional, expensive, tactical, like, wiping paper, which is bar napkin. Okay, and it was dunked inside this. I welded this thing myself. It's like a bath of dry ice and isopropyl alcohol. We glued the memory chip, a single memory chip, onto this head, which is like a copper, heatsink head. And the board that we just put it on is a Cisco IP phone. And this here is a DDR3. This is an FPGA dev board that it conveniently had the exact same memory footprint for DDR3 memory. So what just happened, right? Like, we convinced the computer to turn on. We kept the memory cold. And then at the right time, we pulled it off and put it onto our little ready thing. And we were literally reading its memory. So it's in some cases, like, really complicated how to get this to work. But, like, a 5-year-old can understand this attack. Like, you take the chip and you put it on, you read it, right? So, this is certainly nothing new, but, like, the novelty here is, how do we do it for, like, affordable cost, right? And what are the tolerances? Like, what are the things we can do? So, like, all right, I'm not going to ask any questions. Like, here's the answer, right? So, this is the solution, right? So, I started with this, and, there's no brands on AliExpress, like, they're all from the same place, but this is, like, for what you're getting, an excellent piece of metal, okay? So you buy something like this, and the naming scheme is actually like the length and the width in millimeter. So you can you can just Google the same thing for like an 80/40 or something, and they're generally pretty excellent. Well, okay, so you buy this and you do this. Okay, you junk the controller, you junk the motors, and you junk the thing, the Z-axis, and then you replace it. And part of the reason why is, okay, so this thing on the back literally has a 25-pin like aux port for parallel port, right? This is a modern device made in China today, 2023, and there's a factory of people still like cranking out like the parallel port interface. I don't know why, and I mean the controller is basically useless. You don't need anything even remotely close to this big of a box. The motors are fairly cheap, but the stuff that's really good about this machine is the aluminum is solid, right? And, these are like extruded aluminum. They're not machined, they're not positioned, but they're fairly straight. And what's actually more important is, inside there, right, instead of a timing belt that you see on like a 3D printer, this is an engraver. So this actually has a really high quality ball lead screw, right, which is solid, it's machine polished, it's precision ground, and it's basically the foundation of what we need in order to get precise, repeatable movement on a budget thing. So once we get this machine, right, and also when this comes out of the box, every screw will be a random value of tight, right? You're gonna get a different one, and you think like, man, people can like screw the screws. Nope. You should check every single one because, this thing's been sitting in a factory, right? Like, it's been shipped around and stuff. But the tightness of the screws actually do matter, and I'll get to that. All right. So once you have this machine, so here's the next thing, right? Machining stuff like linear motion and its discontents. So everybody kind of we know this is a stepper motor. It has a few wires. Generally, you pulse a signal, right? And then you have a signal for direction, and given the pulse, it turns in that direction, right? That's what stepper motors do. So another idiocracy thing, right? It's like steppers crave steps. But what is a step? And if you, need something with precision, okay, like this thing is a thing that spins in a circle. We want linear motion, so what is a step? How far does each step go? How do you know? So if you send, pulses for 1,000 steps, and you know that every revolution of your ball screw is 5 millimeters, you can do some math and divide, right? So in theory, every time this thing turns a certain number, you should move precisely 5 millimeters, right? But in reality, it doesn't work that way. And everything that you can think of that can go wrong between like your mind, right, and reality of like the physical linear motion will happen. And here's some examples of it, right? So, and I love this. Like, this is a thing on Reddit. Like, how do I fix my bent lead screw? Right? It's like, and there was probably like 50 comments of like people trying to help, but like, I know the right answer. Get another lead screw. But so yeah, like your lead screw is imperfect. It might be slightly bent. It might not be machined carefully, or like to spec, especially when you have something budget. But as the thing turns, obviously, like there's a mechanical linkage that connects the thing to the thing that actually moves your head backwards and forwards. And if you really start to think about like what a screw is, right? Unless you have a perfectly fitting screw and a nut, you're going to have backlash no matter what, right? And backlash is basically the difference between the angle, right, the edges of your lead screw and the edges of the nut. As you move back and forth, there has to be some wiggle, otherwise the thing won't turn. Anyway, so this goes on and on and on. And the cool answer, like, the nice thing here is there is a good answer for all of this, right? And the right answer is just spend money to buy more equipment that's not garbage, right? So in order to get precise movement, with stepper motors in imperfect sort of mechanical system, right? The answer is just put a linear encoder and get something of a closed loop control versus open loop, right? So closed loop control is, it has basically like a digital or an analog encoder system that moves along with your head. So regardless of how many pulses you send, right, to the motor, this thing will tell you precisely how many millimeters or microns you've moved. And then the next part of the trick is you have to get this perfectly parallel and perpendicular to your workpiece. Otherwise, you're going to have to do you just have to be right, because otherwise your encoder is not really telling you like the precisely motion, right? You're talking about like a little bit of sine and cosine and trig and stuff, and that's not fun. So that's the right answer, but like we're looking for like innovation and compromise-ish, but still getting something that works. So here's a really cool, so like here's like a number of things that I think are game changers in hardware and material that made this thing possible, where I don't think it was possible probably 5 years ago. So maybe 5 years ago. All right, so the number one thing is this is, and there are a number of these things like this, but I like Technic Motors. They're a good company. They make reliable motors. Don't get paid for sponsoring them at all. But what they've done is these things have a microprocessor and precise optical encoder and a lot of analog sensors built right into the motor itself. So the thing is literally running a hard real-time operating system that is doing dynamic control. So you're not getting the linear encoder, but this thing is actually measuring power usage, right, and actual rotational precision. And you can actually write a piece of code that actually calibrates this motor, like with position for the specific lead screw that you have your machine on. And you can actually calibrate it based on the load of the head. These motors are actually overpowered. So if you get one of these, they have 3 lines. I would recommend the SC line, which is the software control line, which gives you full-on API and real-time control. Only downside is they wrote it in the most bizarro Byzantine C++ thing. I don't know, right? It's not simple, but once you get it to work, it's actually very good. It gives you a lot of control, and this is basically, a really good compromise. And each of these is like $400. Well, they start at like $300. These one is like $400, but this is a pair of these is a magical way of converting basically, like a cheap and very sublinear, like substandard linear motion thing into a fantastically accurate one, and I'll show you some videos of that. So that's number one. And there are other, open source versions of this, but basically you want something that has a microprocessor that gives you closed loop control. And once you have that, you're going like 2 orders of magnitude in precision potentially, like with what you can build. So the next awesome innovation, right, is compliant elastomer test sockets, right? So these are amazing. So it's exactly what it sounds like. This is a rubbery test socket that can, run at tens of gigahertz, right? And it is a test socket, but basically it's like a gummy bear kind of like consistent thing. And this is the thing that allowed us to basically create a CNC that pushed the DDR memory down, right, in a way that actually works, right? Because you can imagine, like, without something like this, like, how am I going to mechanically put this DDR memory in like a clamshell, right? And then close it without shorting some stuff and like causing a lot of signal loss, right? So I would say, I think like 10 years ago, nobody was manufacturing these, and these were like at least a few $100s, if not a few $1,000s for custom, things. But today, right, and this was like 2 years ago, or like a year ago, this is on Taobao, right? You can spend this much dollars to get this many custom elastomer test sockets. They custom make them, and I don't know, as far as I think, what they actually do is this is literally 3D printed, and the conductors are just columns doped with very fine silver particles, right? So they can actually do short custom runs, and it's very affordable, and this is the magical thing that allows us to mechanically put memory on and off the thing without cracking the chip, cracking the board. This actually works. Yeah, and it's really affordable. So other things you would need that's not like a game changer is get a nice set of shims. You're going to need them. And then like a big old cup of like patience. Because like I said, when you get your machine out of the box, every screw is going to be a random value of tightness. And, once you do all of the changes, right, you're going to be basically working with reality and like imperfections. So, each of these joints, you got to think through like, if something's actually off, right, like usually they're off by not like a washer, but, maybe like a tenth of a millimeter or even less, right? So a nice set of, stainless steel or brass shims and a big old cup of patience and like a few nights, very much necessary. But it does the trick. So, and the next thing that really made this thing game changer is this clay. So the next thing that we had to solve was how do you keep the board stable and flat on the machine in a way that doesn't conduct, that isn't just, that isn't wobbly, right? I tried to make a urethane casting. It worked, but way too complicated. We tried little clamps. Doesn't work because PCBs, you think they're flat, they're not. Basically, every material like you're going to work with here at this level of, and this isn't like crazy precision, but at this scale, just assume it has the consistency of like somewhere between a Twizzler and a gummy bear, right? Nothing that's solid is really all that solid. Nothing flat is really flat. Things tend to be wavy, and even if you have a tiny amount of pressure, right, you're going to create bowing and such. So, clamps on the side, no go. But this is really good. So this is not clay. This is like an oil-based material. You put it in the oven or like the microwave for like 15 seconds, and it basically has like the consistency, and it looks like very yummy Nutella. And it cools down in like 45 seconds, and it creates a perfect, very solid sort of impression that holds the thing in place. It's awesome. I'm always tempted to eat it, but it's not edible. All right, cool. And then maybe one of the last things is get to know and love your indicators and nerd about metrology. Like, there's a whole lot of things to talk about here, but based on, with this motor, with the control system, and with the shims, right, you get one of these indicators and you sweep back and forth until you have parallel and squareness, right? You gotta be patient, but this is certainly a skill that anybody can learn, with like a night of patient, quiet work. All right, so with all of this stuff, right, after 7 months of failing, this is a kind of what we're going for. We want to mechanically make the system move reliably back and forth and put the memory on and memory off. And, long story short, we did it. So this is the kind of the last video. We took this, like a few days ago. So this is an indicator. So keep in mind, each tick here is 0.0005 millimeters, which is about 12.7 microns. Right? And what we're going to do is, AliExpress hardware with, closed loop motors, and some fine tuning. All right? We're going to move it back and forth, and we're going to see how repeatable this motion is. So we're going to, so right here-ish. That's the first go. Bring it back up. Oh no. Okay. I'll just describe to you what I'm saying. Like, I don't. Okay. Oh, you guys didn't even see the first video then, right? Oh, all right. Well, okay. I feel like there's some context here, so let me show you the first video too. Oh, it's okay. All right, do you see this? Okay. Man, all right. So here's the first video. Like, here's how this thing works. Somebody should have said something. Okay, like memory glued to the brass thing, like a cold tub of dry ice and isopropyl alcohol to the Cisco phone. Then it turns on. And notice, right, the modeling clay, really solid, really stable. And we tried a lot of materials, so that is definitely the one to go. And then, add a specific timing boot, right, pull it off, physically put it onto the FPGA dead board, and read the memory, like, right? And notice how, like, yeah, okay, I mean, it's a video, it's not, like, no surprise there, it works. But, so let's look at this now, right? That was a pretty rough, first go, but now we're talking about, really dialing this thing in. So we stop there, and we're going to back off. Ta-da! So, like each tick is 12 microns, and this is really the limitation of the gear, but yeah, so you can absolutely make this level of precise controlled motion for like $1,000 with hardware that you buy from AliExpress. And with that elastomer socket, you can make a memory extraction system. And the reason why I don't call it code boot, but cryo-mechanical memory extraction, is one of the latest things that we added to this is instead of using that dry ice bath, we built a closed loop cooling system, basically like PC water cooling, but with isopropyl alcohol. It can live off of liquid nitrogen or dry ice. But because of that, we don't just have to like cool the memory, boot, and then hope it stays cold. We can actively cool the memory and pull it off whenever we want, right? So it's no longer just cold boot. It, is actually just cryo-mechanical memory extraction. So you can run it for almost an arbitrary amount of time, as long as you have enough cooling. And, like big old door liquid nitrogen is like $100. It's a lot of cold. It works. So now this kind of opens up all sorts of really interesting questions of, number one, like what else can we do? Can we actually target like application level code? Obviously we can't, right? Like you just have to find the right timing, but it's not just about the bootloader, not just about the kernel. You can pull memory off whenever you want. And the second question, or like 2 and 3, we all know there's a maximum operating frequency for memory, right? does memory have a minimum operating frequency? I mean, it does. Like, that's not the deep answer. But what happens when we can artificially lower, let's say, DDR4 memory to a frequency that we can work with on a affordable FPGA, right? Because if you want like a DDR4 interface on an FPGA, like today, you're spending like a new car money, right? So if there was a way to slow down the clock of modern things like DDR4, how slow can we go, right? So that, I have some ideas. That's really interesting. And then the last question is, this machine goes up and down, right? What if we put the memory back? So, and short answer is like most of the time, if you do it haphazardly, it won't work, right? But if you look at the DDR state machine, right? So that is a dream, and implementation is very chip dependent, but we are playing with this way of actually literally moving memory back and forth, physical memory, right? But you have to do it in cases where the state machine actually lines up. I think it's possible, but that is a thing that we're doing now. So with that, I think I might be a few minutes over. Am I? No. 1 minute. Look at this. Like perfect timing. So, with that, this is my little obligatory sort of advertisement thing. I run a company called Replicant Security. We do embedded security. Himanshu is also here with us. And he actually was nice enough to print out some of the papers from Woot and Host. One of them is behind a paywall. So if you are interested in the paper, hit us up. And, number one, if this type of adventure is what you'd like to work on, maybe you can join Replicant Special Effects Club. And number two, Replicant is a company, we tend to take on pretty, boutique, high-end, difficult embedded security things where we help our customers make their devices, much more secure in this kind of, in not obvious, but pretty awesome ways. So if you are a person who has control over building something that's kind of important that runs the world that wants it to maybe be more secure, call us up, right? We want to work with you. So with that, questions? Thank you. Come on, you got it. Okay, cool. Question? Yeah. Yeah.
I think in the video you read out one.
That's right.
I think you also need to do it probably in a synchronized manner.
That's right. Yeah. So if you're interested, the details of that is in the Woot paper. And what we actually ended up, so that was a Cisco phone, right, for simplicity. What we actually had to do, and this was kind of cool. Like the insight there was either you build a massive machine that pulls 5 things off simultaneously, which is stupidly impossible, right? Very expensive and almost impossible. Or the insight was if we can find periods of execution that is CPU bound, guess what? The computer is not doing when it's CPU bound. It's not writing to memory, right? So we took out a near field probe and, we did a lot of, in the past we have quite a bit of experience in, exercising and working with compromising emanation. So we basically, spectrum analyzer, right, near field probe and mapped out timing windows of literally tens of milliseconds where we have CPU bound operation, where we have memory stability. So that's how we kind of cheated the timing requirement.
Very cool. Thanks.
Good question, though.
Any other question? No? You're good? Thank you.
Really? Okay. All right. Thank you.